Hey everyone, and welcome to this explainer. Today, we're diving into the secret double life of a component that literally built the modern world, the Bipolar Junction Transistor, or BJT. We're going to break down its split personality, and then we'll throw in a massive plot twist that totally redefined how we think about electrical control. Let's get into it. So here is the big mystery we're unraveling today. How exactly does a single tiny piece of silicon, made of just 3 doped semiconductor regions, know whether it's supposed to delicately boost a smooth audio track or violently slam a digital circuit shut? Well, it all comes down to how we drive it. We either treat it as a linear amplifier or as an electronic switch. All right, identity 1, boosting signals, the amplifier. Now, before we look at the BJT acting smoothly in its linear region, we absolutely need a quick decoder ring for the math. Mixing up AC and DC is a total disaster for circuit analysis. So remember this rule of thumb. DC quantities use italic capital letters, like a big I with a big C. But the AC quantities, the actual moving, time-varying signals we're trying to amplify, they use lowercase italic subscripts. It's a simple rule, but honestly, it's absolutely essential to keep straight. Okay, so what is amplification anyway? At its core, it's just linearly increasing the amplitude of a signal. We express this as voltage gain, or A sub V, and it is literally just a ratio, the AC output voltage at the collector divided by the AC input voltage at the base. So if you feed a tiny 1 millivolt signal in and you get 100 millivolts out, boom, your voltage gain is a solid 100. But what's physically driving that gain under the hood? Well, voltage gain is approximately equal to the external collector resistor, that's RC, divided by the internal AC emitter resistance, R'E. Because that forward-biased base emitter junction has a really low internal resistance to the AC signal, we can use an external collector resistor that is way, way bigger. That massive contrast in resistance, that's exactly why the output voltage explodes compared to the input. Let's switch gears. Identity 2, on or off the switch. So if the amplifier was like a smooth volume dial, the switch is, well, a rigid light switch. When we jump into digital circuits, the BJT completely abandons that linear active region. On one extreme, we have cutoff. Just picture a heavy locked door where absolutely no current can get through. Because the base current is sitting at 0, neither junction is forward biased. Aside from some microscopic leakage, the component is just entirely blocking electricity. Then, on the absolute opposite end of the spectrum, we have saturation. Here, both junctions are forward biased. The door is kicked wide open and highly conducting. The collector current hits its absolute physical maximum and completely ignores any further increases in base current. Basically, you've pumped so much current into the base that the transistor acts like a solid piece of wire. If you picture this as an ideal model, it makes total sense. With 0 volts at the base, it acts perfectly like a broken physical circuit, just completely open. But the second you push a strong enough positive voltage to that base, we hit saturation. It snaps into acting like a closed switch, shorting the collector directly down to the emitter, so maximum current can flow. And this strictly binary behavior? It's the entire foundation of digital logic. Let's summarize it real quick. In cutoff, base current is 0, and the voltage from collector to emitter equals your full supply voltage, meaning it's fully blocking. In saturation, your collector current maxes out, and that collector-emitter voltage plummets to practically 0. It is either completely blocking or completely flowing. There is absolutely no in-between. So, how do we use this in the real world? Easy. We just bounce between these two extremes by feeding a square wave into the base. When that square wave hits its high voltage phase, it forward biases the junctions, saturates the BJT, and turns it firmly on. Then, when the wave drops instantly back to 0, the base current vanishes, which cuts off the BJT and snaps it off. Put that exact behavior into a real circuit, and you get perfect, reliable control. Alternating that input perfectly blinks an LED, for example. During the high pulse, the transistor snaps shut, current rushes through the resistor and the LED, and let there be light. During the low pulse, the transistor opens, the current hits a wall, and the light dies. It is just clean, simple, binary control. All right, are you ready for the twist? Seeing light, the phototransistor. So here is the plot twist. What happens if we completely change how we control that base current?
Up to this point, we've relied on physically pumping electricity through a copper wire. But what if we could control a transistor without any wires connected to the base at all? I know it sounds a bit like magic, but this exact question leads us directly to the phototransistor, a component that converts light energy directly into an electrical signal to steer the circuit.
If you actually look at standard phototransistor packages, you'll immediately notice something is missing. A lot of them only have 2 leads instead of 3. Instead of a wire for the base, there's a tiny lens or a glass window that lets light enter the package. That light totally replaces the traditional electrical base connection. In fact, the base isn't even electrically available to hook up to. The whole device is piloted entirely by light. The physics behind this are just brilliant. Light enters that lens and strikes an exposed collector-base PN junction, which is specifically designed with a huge surface area just to catch those incoming photons. That light energy actually generates a base current. And then, exactly like a standard BJT, that light-generated base current gets multiplied by the transistor's DC beta. So the brighter the light you shine on it, the higher the collector current goes. You can see this play out perfectly on the characteristic curves. Instead of plotting electrical base currents, these graph lines actually represent varying levels of light intensity. As that light intensity scales up, say from 10 up to 50 milliwatts per square centimeter, the collector current rises right along with it, proportionally. It behaves exactly like a conventional BJT, except photons are the ones doing all the heavy lifting. And these light-sensitive switches, they are literally everywhere. They range from basic light-operated relays to incredibly clever components called optocouplers. An optocoupler actually places an LED and a phototransistor inside a single sealed black box. It uses light to electrically isolate 2 totally different circuits, letting them communicate perfectly securely without a single physical wire bridging the gap between them. Honestly, these foundational behaviors power our entire digital age. We've just seen how a few tiny junctions of doped silicon can act as a smooth, delicate amplifier, a rigid binary switch, and literally an eye for invisible light. Which kind of makes you wonder, what other invisible mechanics are operating silently in the devices you rely on every single day? Thanks for joining me on this explainer, and keep looking deeper into the circuits that run our world.